Now that we've discussed the clays in condensation, let's talk about what we can do with these beta-keto esters that we've been making. So these compounds and ones related to them are useful in a process known as the Malonic and Acetoacetic Ester Syntheses. The starting materials for these syntheses are malonic esters like diethylmalonate, acetoacetic esters like ethyl acetoacetate, or other beta-keto esters. A wide variety of different molecules can be used in reactions like this. The way this process works includes 3 steps. Starting from diethylmalonate or any other similar compound, we will first treat with a base, followed by treatment with an appropriate electrophile. Here I've shown an alkyl halide, followed by aqueous acid and heat. The products we get are a substituted carboxylic acid or ketone, and CO2, and the ester group which we've cleaved off here. So how does this process work? Let's go through each of the steps one by one. In the first stage of this process, we take our dicarbonyl compound and we treat it with a strong base like sodium ethoxide. Doing so will generate this doubly stabilized enolate. The carbanion shown here can be delocalized through both of the oxygen atoms. This compound is a fairly good nucleophile, and that's how we're going to be using it in this process. We'll then take this nucleophile and treat it with an appropriate electrophile. Here I've shown an alkyl halide, but there are many, many other possibilities to give this substituted compound as the product. Note that this alkylation reaction here proceeds through an SN2 mechanism, so our alkyl halide must be appropriate for this. It should be primary and unhindered, or it should be methyl. Other electrophiles are possible, many of which we'll see some examples of as we continue. The third step of the process is the most interesting. What we're going to do here is we're going to take this diester and treat it with H3O+ and heat. You might recognize this from our previous discussions as hydrolysis of the ester. So we will indeed hydrolyze the ester to get this dicarbonyl group here, but something else will happen after this. Compounds like this, when heated, will lose CO2, a process known as decarboxylation. What is the mechanism of decarboxylation? Well, if we start with a compound like this, one that has a carbonyl group which is beta to a carboxylic acid, notice that I've only referred to the carbonyl group here. This could be another carboxylic acid, it could be a ketone, it could be an aldehyde, any other member of the family will suffice. We can rotate this around to get to a more stable conformer, which is stabilized by hydrogen bonding. The carbonyl group, which is hydrogen bound to that hydrogen, will then cause a paracyclic reaction to happen, which will eject CO2. Since we're ejecting a compound which is a thermodynamically stable gas that will rapidly bubble out of solution, this process is irreversible. The compound I've generated here is the enolate of a carboxylic acid, which will rapidly tautomerize back to a substituted carboxylic acid. This is an especially useful process to produce substituted carboxylic acids, as carboxylic acids are far too acidic to form enolates efficiently. The real utility of this process is in synthesis, building complex carbon-containing derivatives from simpler pieces. For instance, if we were to walk through the synthesis here of this compound starting from ethyl acetoacetate, where would we start? How do we analyze this problem? Well, first, we can locate the 3 carbons which are going to be derived from acetoacetate. It's these 3 on the left containing that carbonyl group. We can then identify disconnections at the alpha position to identify the electrophiles that we'll need to add during the process. Here's one, and here's another. We can then work backwards to draw the product of our process before decarboxylation has occurred. Remember that the ester group from our starting material is going to be lost to CO2. Now that we've done that, we can step through the process and add our 2 groups, the green and the red alkyl groups, one at a time. So we would start by first treating this compound with a base to generate the stabilized enolate. Then we would add the appropriate alkyl halide to add one of our alkyl groups. We would then repeat the process to add the other alkyl group. Finally, the way we would finish the process is by treating this with H3O+ and heat, which would hydrolyze the ester and cause decarboxylation to give our final product. Let's do one last set of practice problems where we draw the product of each reaction sequence. Take a look at these 3 problems, work your way through them, and then we'll compare notes when you're done. All right, to start, I'm going to be walking through these sort of one little piece at a time to see what happens. In the first case, we treat our beta-keto ester with sodium ethoxide to generate an anion, which will then open up this epoxide as electrophile. So since this is open the epoxide, we have our 1-2 pattern in our product, where we have the alcohol group separated from where we formed our new carbon-carbon bond. In the second reaction, we would treat diethyl malonate with sodium ethoxide followed by this electrophile to form this haloalkane product. Notice here that this thing can react internally, which means that we're going to expect a ring in the second part of this process. Finally, for the third example, we alkylate it once with a methyl group and a second time with an ethyl group to produce this product. Now with this sequence, the next thing that's going to happen is reduction of those carbonyl groups. In the first reaction, we follow up with hydrolysis and decarboxylation to give this keto alcohol as the product. In the second reaction, we remove the second proton, react internally, then hydrolyze and decarboxylate to give this substituted carboxylic acid. In the final reaction, we reduce the two ester groups to give this diol as the product. Next, we're going to see another application of these nucleophiles when added to alpha-beta unsaturated carbonyl compounds, the products of aldol reactions.